So we started with the definition of fields. Here's the definition of a field. It has two operations. They have to be well structured, they have to be commutative, associative, stuff like that. And for us, it was important that the field is closed to addition and multiplication, which means that if you have the A and B in the field, then the sum and the product is also in the field. And we saw examples, the real numbers, the complex numbers are all fields. For us, the most useful for this discussion is the rational numbers, which is fractions with the integer numerators and denominators. Okay, so we did all that. Let's go immediately to the summary before the geometry part. Okay. Yeah. So we saw about fields. And the main tool that we've been using is field extensions, which is basically taking a field and you introduce a new member to this field, like square root of 2, which is not a rational number like we saw. And the implication is that you have to add more members just to make the field closed again. So if you add I to Q, Q is the rationals, you get a field extension Q adjoined I, that's the term. Which includes not only I, but all values of the form A plus VI, where A and B are from the basic field of rational numbers. Another example you see here is if we adjoin take the rational numbers Q and we adjoin the fourth root of 2, we get this structure of values. This is what we call the vector field, which is of dimension 4 in this case. The basis of this field, vector field is these 4 values: 1, fourth root of 2, fourth root of 2 squared, and fourth root of 2 to the degree of 3. So these are all linearly independent. So it's a valid basis for a vector field. Okay, and the degree of the field extension. So this is a field extension. So we have 2 examples here. The degree of the field extension is the size of the basis of this vector field. So in this case, the first example, Q adjoined I, is of dimension 2, because there are just 2 elements in the basis, 1 and I. And the second example here, Q adjoined fourth root of 2, is of dimension 4, because the vector field has 4 elements in the basis. And then we saw that another definition for the degree of the field extension is the minimal polynomial of the root that you add to it. So in this case, in this example, we added the fourth root of 2, and the minimal polynomial of the fourth root of 2 is here. It's x to the power of 4 minus 2, and the degree of this polynomial is 4, and therefore the degree of the field extension is 4. So we have 2 definitions, equal definitions to the degree of the field extension. One is the size of the basis of the vector space, and the other is the degree of the minimal polynomial of the root which we added. And then we saw the Taylor law, which basically talks about what happens if you have more than one root to the field extension. So in this case, if we add n roots to the rational set field Q, we can add them in any order we like. It doesn't matter. We get the same field extension. And the degree that you get, according to the Taylor law, is the product of the degrees of the minimal polynomials for all these roots. So you just have to look at all these roots, find the minimal polynomials, take the degrees of these polynomials, multiply the degrees, and you're guaranteed to get the degree of the resulting field extension. And this is actually what we wanted to. The whole algebra that we did was to get to this law, which is we're going to use now in the proof. Okay, so again, I think I talked about this also, but there was some ambiguity. So I recap again. So get a definition of what it means to be for a point in space in the plane to be constructible in one step from a set of other points S. So the game is like this: you have a set of points S. You can make as many circles and lines as you want from this set of points. You can draw lines with a ruler between pairs of points. You can make circles around points and so on. You can make them as many as you like. It doesn't count as a step. The only thing that counts as a step is if you add a single extra point to your set. So you can, while you're doing all these lines and circles, you're not adding any points. But at some point you can stop and take a look at some intersection between lines and circles, and then introduce this new point into your set. And this is considered a step. So you get circles and lines for free, but whenever you add a point to the set, that's considered one step in the process. And the point P is constructible in one step if you abide by these rules. So you can do as many circles and lines as you want, and then you stop and add one point to your set, and that is constructible in one step. Obviously, P is constructible in many steps if you just repeat the process. So you start from a set S, you construct point P1 in one step, and then you construct point P2 in one step, and every point on the way you can also use the points that you already constructed before. And if your set S happens to be the plane of points with rational coefficients, that's Q times Q here, then the point is considered constructible, just like that. Okay, so an example again. So I think we saw this geometric construction before. So if the set S is the points A and B, so you construct P1 is considered constructible in one step from A and B, because you can put all these circles and lines that you see here, and then you can take P1 as the intersection of the two circles. So that is, the P1 is constructible in one step, just for A and B, even though we did many circles and lines just to get them. But once we have P1, you can similarly construct P2, actually using the same circles and lines. And then we can, once we have P1 and P2, we can draw a line between them and find the intersection between this line and the line AB. And then P3 is also constructible in one step from AB, P1, and P2. And P3, since it's the end of this sequence of constructible points, P3 is constructible from the original set AB. And if A and B happen to be rational numbers, then P3 is just constructible. Okay, so that's just the definition of constructible points. Okay, and I think we saw this also. So we have we start from the field of the plane of rational coefficients. We start with the point P1 with coordinates x1 and y1. And then we add construct in one step the point P2, and so on and so forth, until we get to the final point that we want to get to, which is P, which happens to have coordinates x and y. So we have a sequence of points. Each is constructible in one step from the previous points, and each has two coordinates. Okay, and now we define for every point on the way, we define associated field or field extension. So we start with the field K0, which is just the rational numbers, the Q. And then for the point P1, we adjoin to the rational numbers the coordinates of P1. So we adjoin the x1 and the y1. And so actually we adjoin two values, right, to the original K0. And then we go to the second point, P2. Again, we adjoin to K1, we adjoin the coordinates of P2, which are x2 and y2, and so on and so forth. Until we get to the end, we get to the final field Kn, which is all the coordinates of all the points we saw before, and also the points x and y, and the coordinates x and y. And for each of these Ki, we said that it is associated with the corresponding point Pi, which was on the way to the final point. And then we saw that we want this lemma, we proved this lemma, that for every Ki, it's the dimension of the field extension Ki on top of Ki minus 1 is always 1, 2, or 4. Okay. So there are actually three cases. The case one is that we got the point xy as an intersection between two lines. The other two cases are between a line and a circle and between two circles, but let's start with this case. So x and y is the intersection of the two lines. The two lines, you see them here, you have the points A and B and points C and D. You have to elongate the line, the section CD to get a line, and then you find the intersection PI between these two lines. Now, the A and B and C and D are all already inside Ki. We got them before. We constructed them before in several steps from the original set. So all we do here is just add a new point pi based on these known points and coordinates. So all the coordinates of the 4 points, xa, ya, xb, yb, and so on, are already inside the original field extension ki, and we want to compute the coordinates of the new point xi, yi based on these 2 points. And this just happens to be you have to compute the determinants, you have to divide the determinants, just two linear equations which you want to solve. And computing determinants and dividing them just involves addition, subtraction, multiplication, and divisions. And so all these operations are all available in the field. You don't have to do anything. And since all these coordinates are already inside ki minus 1, and ki minus 1 is a field, so it's close to all these operations, and therefore the new coordinates of the intersection point of pi are also guaranteed to be already in the set in the field ki minus 1. In other words, ki minus 1 is good enough. It already contains the intersecting point, and you don't have to add anything to get ki. And when this happens, the dimension of ki over the equal ki minus 1 is just 1, because it's just one coefficient. Okay, so we proved the lemma for this case. It was just happened to be 1, and 1 is 1, 2, or 4. The case number 2 is a bit more difficult, not much, but we have in this case we have a section, we have a circle around the C. We have we have a circle. We have the radius of this circle, which is the distance between the given points D and E. And we took the compass, we grabbed this distance between D and E, and we drew a circle around C, the given C. After having done that, we have the points A and B. We draw a line between A and B, and we want to know what the intersection is between this line AB and the circle around C. Okay, so as before, all the points here except pi, so we have the A, B, C, D, and E, are all inside the previous field, ki minus y. So we have all their coordinates. We have 10 coordinates listed here, already in the field ki minus 1. We also have C. That's right. And the thing that we also have is the square of the radius, right? Because by the Pythagorean theorem, the R square is what is written here, which again is just involves multiplications and additions of values that are already in ki minus 1. So in other words, ki minus 1 already includes R squared also. So ki minus 1 includes all these coordinates and R squared. Okay. So now x the x coordinate of the intersecting point pi. It just happens to be the equation of how you can find it. You have to trust me on that. But the important thing here is that this is a quadratic equation, right? It has x squared there somewhere, and all the coefficients, all the values that you see here are all constants, which are already known available in ki minus 1. So as far as we care, they are all just numbers. We already have them in ki minus 1. You can compute all the coefficients just using the closure properties of ki minus 1. They're all already in there. So basically, we have you can say that this is a solution to a quadratic equation where all the coefficients are already in the field. That's just like saying that the minimal polynomial for x is quadratic, so its degree is 2. And therefore, if you just adjoin x to the previous field ki minus 1, you get a field extension of degree 2. Again, because the minimal polynomial has degree 2. And the same goes for y. If you add y, adjoin y has a similar formula. So again, the field extension, the degree of the field extension adding y is 2. And according to the Taylor rule, if we have 2 points, you just have to multiply the 2 degrees, and you get 2 times 2, which is 4. So this is 4, but actually it's also possible that we get 1 or 2 in this case, because it could happen that when you want to find x, the solution to this equation is a value x which is already in ka minus I minus 1. You already have it in some of the points that you created earlier. So when that happens, when you add the x coordinate to ki minus 1, again you get the same field, and the degree will be 1. And the same could be for y. If y happen to be already a coordinate available from past points on the way, then again this will be the degree of 1. So if both are new points, x and y, you get 4. If one of them is new and the other is already existing, you get the degree of 2. And if both already existed, then you get the degree of 1. So the lemma holds. It's the degree, the final degree of the field extension ki over ki minus 1 is 1, 2, or 4. Okay. And the final case that we have is in intersection of two circles. So here you see equation of circles. You have two equations for the two circles. You want to find the intersection between these two circles. So if you can just subtract the two circular equations. So this also must hold, and this happens to be just an equation of a line. So again, if you just subtract two simple equations, you get an equation of a line, and this happens to be this dashed line here. So the intersection between the two circles is just the intersection between the dashed line and any of the circles that you like. So we're back to the case we saw before. So to find the intersection between two circles, you end up looking for intersection between a line and a circle, and we did that before, and we saw that the lemma holds. So the degree will be 1, 2, or 4. It will be the same here. So again, in the third case, the degree of the field extension of that occurs when you have an intersection of two circles is again 1, 2, or 4. So in all three cases, our lemma holds. So if you go back to the original slide, so we have a sequence of points, a sequence of field extension, associated field extensions, and for all these field extensions, the degree of any field extension relative to the previous field extension is 1, 2, or 4. And now is the time to apply the Taylor law for the whole thing. So if we started from Q, K0 is Q, we ended up in Kn, and we just, you remember the Taylor law, it's most convenient to read it from right to left. So we start from Q, we go to the field extension K1, and the second step we go from K1 to K2, and so on and so forth, until we reach Kn. And the Taylor law just says that the dimension of the final field extension from Q all the way to Kn is just the product of all these pairwise field extensions. And we just saw by our lemma that all of these smaller field extensions has a power of 2, actually 1, 2, or 4, and therefore the whole field extension from Q all the way to Kn is a power of 2. But this is actually not exactly what we wanted to prove. We want to prove that just adding one coordinate to Q is also a power of 2. Here we actually made much more than that. We started from Q, we did many coordinates of many points on the way, and we got a field extension Kn, and we just proved that this Kn has a dimensional power of 2. We just want to make one small addition. We take Q with just a coordinate of the final point on the way, x. We also want to ensure that also just this point also has a degree, the extension of this field extension also has a degree which is a power of 2. So we're almost there. Okay, I'm just rewriting the same equation again. So Kn over Q, again by the Taylor law, I can make it, instead of taking all the steps of the way, I can just do it in one hop. I go from Q, I just add one value, the x coordinate of the final value of the final point. And then from Q adjoint to x, I somehow make all the way to Kn, similarly to what we did here. Okay, we already know that that Kn over Q is a power of 2, and therefore, and since it's a product of two integers, and both these integers must also be a power of 2, and therefore, this is what we wanted to show. So if you take the rational, the field of rational and just add the x coordinate of the final point, you get the field extension, which is a power of 2. And this is what we actually wanted to achieve. So let me summarize. If you construct points using ruler and compass, any x coordinate of any new point that you get on the way, the field extension of just the rationals with just this x coordinate will give you a field extension of which is a power of 2, of dimension which is a power of 2, and that's enough for us. So let's go to the fun part. So we said we have three impossible things. One of them was given in a cube, let's say of side 1. So this point here is on coordinate 1.0. I'm missing the z coordinate, but let's forget about that. And I want to construct a cube which is of double volume. So this point P, which I presumably am able to construct, has a coordinate c of the x coordinate is going to be c, and the c cubed must equal 2 because it has double volume. The original had volume 1. This has to have a volume of 2. So this c, which I actually constructed, is a solution to this equation. It's x to the cubed equals 2. So in that case, the field extension q adjoined c, I just add this value here to the rational numbers, I get a field extension which has to be 3 because the 3 is the degree of the minimal polynomial, which is this one. And 3 is not a power of 2. So okay. So this actually proves that I cannot create this point C, and therefore I cannot double a cube. Is that clear? Okay. Okay. Let's look at impossible problem number 2. Claim that I cannot trisect any given angle with a ruler or compass. So again, some angles can be trisected.
Sorry for taking you back. If you go back to the cube example, so this happens in 3D. So your proof worked on in 2D. So how do you extend the proof of 2D to 2 dimensions?
Good question.
So your entire tool set is different, right? Because in 2D you had a ruler and a compass, but here you have like a plane, or what do you have?
Yes, you're right. I should have given the variation of the proof that works for 3D, but it's exactly the same. So if you take the sequence of points with 3 coordinates, you can also show that and the field extension would have 3 coordinates. So every step you take the previous field extension and add 3 values to it. Again, you get solutions to 1, 2, or 4 degree equations. So you're right. It's I kind of tricked you, but it's going to be the same, basically the same proof. Okay. Okay. Good question. So this again, the second example is I want to trisect any angle. It is, by the way, possible to bisect any angle, but it's evident now shown that it's impossible to trisect any given angle. So some angles can be trisected. So for example, 90 degrees, but it's very simple to construct a triangle with a degree 30. Just one side is the half of the other side. It's but for 60, it's a problem. So let's see why. So let's say you have 60 degrees, and you somehow are able to trisect the angle. So you can take this. Let's say you do it on the unit circle. You take this intersection point with the degree 20 segment, and you project it on the x-plane, which is possible to construct. And then you somehow actually constructed the cosine of 20 degrees. And the cosine of 20 degrees just happens to be a solution to a 3-degree equation, and this is it. Okay, so by the rules of trigonometry, the cosine of 60, which is a half, can be written as cosine of 3 times 20, which is this is a Chebyshev formula for cosinus 3 times an angle, and this is just a 3-degree equation. So again, the value to be somehow constructed happens to be a solution to a degree 3 equation, and 3 is not a power of 2, and therefore you cannot construct it with a ruler compass. Okay. And the final problem, which we wanted to show that you cannot square a circle. So you are given a circle with radius r and radius r, and you want to create a square with the same area. So the circle has an area pi r squared, which is pi in our case. So each edge of the square would have to be of the square of pi. So presumably we are able to construct the point P, which has an x coordinate square root of pi. And if that is the case, we can also construct a point which has a coordinate pi, because if you remember, I told you that you can do any arithmetic that you like with add, subtract, multiply, and divide, just using constructible points. So if you have a square root of pi, you can just multiply it with itself and get pi. And the thing is that pi is not you cannot construct. So if you did that, it has it would imply that that pi is that the degree of this field extension q and pi would be a power of 2, but that would mean that that pi is a solution to some minimal polynomial of degree which is a power of 2. Actually, some reducible polynomial of power of 2, and that's impossible because pi is transcendental, and transcendental numbers are not a root of any polynomial. Okay. So actually, I kind of trick you here because again, proving that pi is transcendental is the final step of the proof, and it's a very, very long proof, and this was the final step that actually made it possible to show that you cannot square a circle. I will not show it here because it's very long and quite boring actually, but this is the final punch. So it is because pi is transcendental, which is pretty hard to prove, that we know that you cannot actually make this step of creating a circle, squaring the circle. Okay, but anyway, if we believe that pi is transcendental, then you cannot construct p, and therefore you cannot square the circle. And that's it.